Good afternoon, everyone. My name is James Kerr, and I am the Marketing Manager for our HOOPS product at TechSoft 3D. And today's webinar is titled Engineering Graphics in the Modern World. And our special presenter today is Gavin Bridgeman. He's the VP of Products at TechSoft 3D. And we have a very exciting presentation today that should last about 45 minutes, and we also have a 10-minute technology demonstration. And how the webinar is going to work logistically is you can type questions to me during the presentation into the GoToWebinar question dialog box, and I will field questions with our presenter as we get going. So thank you for attending, and we'll get started with Gavin.
Hello, thank you, James. So, yeah, I'm going to talk about engineering graphics today, and before I kind of talk specifically about our products, what I wanted to do is kind of talk about what engineering graphics means and what it means to TechSoft. So I'll start off talking about that. Then I'll talk about the why and why we feel kind of engineering graphics is so important and so we invest so much in this area. And then I'll talk, after kind of talking generically about engineering graphics, I'm going to talk a little bit about general trends in the industry and more particularly around graphics. You know, we rely a lot on the hardware on your devices for getting the kind of great graphics we present. And so I want to talk a little bit about some of the trends in the industry. And then at that point, I'll kind of, now that I've kind of set the framework and set the context, I'll talk specifically about two of our products, namely HOOPS Visualize and HOOPS Communicator, and talk about those in the context of some of the things that I mentioned around engineering graphics. At the end, we'll have Jonathan, who's going to come in and hopefully give us some cool demos, and then I'll wrap things up. Certainly, this is meant to be interactive, so feel free to post some questions, and I'll kind of, a couple of logical times during the presentations, I'll stop and try and answer those. So let's jump on and talk about what engineering graphics is. And the reason we're talking about this is that, you know, graphics is we really see 3D graphics really in almost all facets of our lives today. Certainly you're seeing it in the entertainment space. Certainly you see it in the gaming space and our kids playing games these days. But engineering graphics is a little different than that. And when you kind of look at engineering, you know, one of the really big important parts of engineering graphics, say, particularly in that design phase, is 2D. And you know, when we think of engineering graphics, we tend to think of the mechanical model on the right-hand side, which is a pure 3D model. But really, what's equally important is 2D data. And you know, real expectations around how 2D looks in your application is really pretty high today. People want the kind of 2D to look like what they see in Acrobat. So they want the lines to be crisp. They want the text to look really, really good. And that's actually a pretty challenging thing to do today, particularly because we're leveraging these GPUs on these devices and are really targeted more at the gaming industry, which is a pure 3D world. So 2D is a really important part of supporting engineering graphics today. One of the very interesting things, and as I kind of talk through this morning, I'm going to kind of move through different vertical markets with initial focus on the manufacturing industry. But if you look at that initial design phase, there's been this great, what they call the, you know, in the model-based definition movement in the manufacturing industry. You talk about Industry 4.0, more in the building and construction space. But what you've seen is you've seen a marriage of 2D and 3D coming together. So now you have people wanting to have their 3D model and they want to annotate that in 3D space. That might be to help create a drawing, but it might also have a fully annotated 3D model. And having this marriage of both 2D and 3D working together actually is a pretty challenging thing to do, particularly when you think of the level of interaction that people want with this data. They want to be able to select on this text. They want to edit it. And in some cases, the text has got to behave like regular text where it maintains screen alignment and a specific size regardless of zoom level. In other cases, they want it to act like regular 3D geometry. And getting these things working together is relatively challenging to do. Also, people want to put in section planes and cut the geometry and have this automatically section the geometry, which again is kind of challenging things to do. So if you just look at that design phase, this getting 2D and 3D working independently and also together is a fairly challenging thing to do and a really important part of engineering graphics. Kind of looking at that spectrum in the manufacturing space, another really important market is the analysis space. You have the CFD where they're looking at fluids, or the CAE where they're looking at structural. And this market is actually bigger than the design market. And it comes with its own set of challenges from a graphics standpoint. In the pre-processor standpoint, people really want to see the full meshing of the model. They want to look down and be able to select down at each one of these elements in the model. They may want to select on these edges. And they really want to fine level interaction with the model at a down at a vertex and at an edge level, which creates some challenges, not just on the rendering side of things, but actually selecting and editing on that geometry. As you kind of move into post-processor effects, people want to put color ramps on data. They want to have legend bars in the scene, and these are have their own set of challenges. The nice thing in this specific area is that a lot of this capability and getting these color ramps applied to things, you can leverage the underlying texture and capabilities of the graphics hardware, which means that you can really get pretty large models and get very good performance with them. So that's kind of like the engineering space. We kind of move beyond the analysis space. A recent market that's a very strong market for TechSoft, we have a number of customers in this space, is the metrology space. And the metrology space is very interesting as the industry is introducing measurement more and more into manufacturing processes. They want to read in these CAD models. In many cases, they want to look at the PMI data so that they can actually use that for coming up with automated measurement plans. So in this world, they're not necessarily authoring these MBD models, but they certainly want to bring in these MBD models, see the annotations that are associated with it. And then the part that gets really interesting here is that they're doing analysis on the model. So they may have a point cloud that they want to display with the model. They may actually have touch points. And in many cases, they actually want to, after they do their measurement, they want to display these very sophisticated annotations on the model. And in many cases, these annotations are very sophisticated, and they build them with user interface elements. So they might have, for example, a HTML canvas that has their annotation like the example you're seeing here on the left, or they may build it with a, an old an MFC dialog. But the interesting part of this is that you need to be able to connect that object back to the 3D model with a leader line. And having this ability where you have a connection between user interface elements and the 3D model, again, is a nuanced thing in the engineering space, but the kind of things that you need to be thinking about when you're thinking about engineering graphics, so being able to connect data outside of the 3D window back into the 3D model. One thing that's kind of just as a little side note that I thought would be interesting to talk about would be point clouds. And point clouds is something that you see a lot in this metrology space. And one of the things that we do in 3D graphics is we leverage the ability that the hardware can do lighting. So if you insert a light into a scene and you have a normal on your surface, the underlying hardware will automatically create a shaded 3D model. Well, one of the challenges with point cloud data is generally it doesn't come with a normal, and so you can't do lighting. So your typical engineering graphics model is on the left side, is this example on the model where it's a solid model and you can't really see any depth. Well, if you're kind of looking at, there's some algorithms that are come out, and we have an IDOM lighting algorithm where you can actually leverage the shader and write a custom shader that can deal with point cloud, and suddenly you can have a depth-based model, even though you have just a point cloud without any normals or without any lighting data. So these kind of things, you really can leverage the power available at the GPU and use some of these shader techniques that are used a lot in the gaming industry and bring compelling graphics into the engineering space. The part that I've mainly been talking about, the manufacturing space, and a lot of the same is true in the building and construction place or the process and plant. They have similarly got various within those verticals. They have sub-verticals, and so for example, in the building and construction, a big part of that market is quantity takeoff, and a lot of the challenges that are needed by manufacturing are quite similar to the needs of building and construction and process and plant. The one difference is that I think a challenge across all these industries is that files and models are getting larger, and so really being able to handle the scale of these larger models is a really important part of providing a solid engineering solution today. The one difference is that in the manufacturing space, you're tending, and the analysis space, you're tending to have low object counts, but the per object triangle counts are really high. So you might have an assembly that only has 5,000 objects, but some of those objects might have 2 or 3 million triangles. In the engineering space, you're really talking about some construction projects that will have millions of objects, but each object might only have on average the median triangle count is basically a wall, which is usually around 12 triangles. So it's the same kind of problem, but kind of different kind of underlying data. And if you don't have a system that manages that, it's hard to move between these different domains. And the last thing that I would just mention before I kind of start talking about why this is important is the interesting thing is you can see there's a lot of people as these markets, we're in the engineering software market, it's a very mature industry, and as a result there's some consolidation. And so you're, for example, starting to see analysis is now part of SolidWorks. And so as you see this consolidation across the industry, it means that each one of those systems needs to be able to handle and view the data from adjacent markets. So that's why having a full-featured engineering graphics data that can serve the needs of everything from CAD through to analysis, through to metrology, through to CAM is really, really important, and something that one of the problems that we're focused on trying to solve. So that's kind of talking about what we see as engineering graphics and the problem that we're trying to solve at TechSoft. Now, I just want to talk about why this is important. And I think this really comes back to, there's, in the last 5 years or 5 to 10 years, there's been this really strong focus on the user experience. And, in the engineering software world, there's no getting away that the biggest part of the connection between our users and our applications is the 3D model and the 3D window. And so this is really what's driving the importance of having really strong engineering graphics. And generally people in the engineering software community, they're very focused, they're generally in a professional environment, and as a result, the things that are actually most important to them are being as efficient as possible in their job. So some of the things that are really important that we focus on, number one, is performance. And performance is not just about frame rate, and that's certainly a big part of it, but it's about how quickly you can open a file. It's about how selection works and how fast that is. And frame rates, of course, are an issue. And a lot of performance is tied to your memory usage. And so from an underlying standpoint, when you're getting this large and large data, you really need to be efficient about how you use data. And you have these very powerful GPUs on your device, but they have a finite amount of memory on them. So you need to be smart about when you use that and how much you take it. And so performance is a number one driver, I think, for us in the engineering software community. And if you're providing an engineering graphics solution, that's really a strong driver of what you're doing. But second to that, people do want to have high expectations around how it looks. a lot of it is in some of these lighting algorithms. And you should be able to do shadowing. You should be able to ambient occlusion. And there's a lot of, in that area, there's really a huge amount of innovation in the gaming industry. And some of those capabilities we can bring into our world. But it goes beyond that. And, sharp text, lines and edges looking crisp. Being able to support these high-resolution devices. You're looking at, on a Surface Book, it has a 280 DPI monitor. So you're talking about these high-resolution devices, and one of the techniques you use for getting high-quality rendering is anti-aliasing. Well, on these high-resolution devices, if you're not careful about how you do anti-aliasing, you can really start running into memory issues, which ultimately hits you on performance, which is a big pain point for people. So that's why we really feel that engineering graphics is really, really important, and more important today than it's ever been, as people really do focus on this user experience part of their application. So that's the kind of what engineering graphics is, why it's important. Before I kind of go on and talk specifically about our products, I wanted to talk about some of the trends that are happening in the graphics industry. Some of these are specific to engineering software, but some of them are just about graphics in general. When we're talking about engineering graphics and engineering applications, we really are talking about applications which are harnessing the power of the GPU on the desktop. So we're very fortunate that 3D is mainstream, and we have these extremely powerful pieces of hardware, our GPU on these devices, and we get to be able to leverage those through OpenGL and through DirectX. And what's been interesting there is that every 10 or 15 years there's been an evolution. So in the early 90s, OpenGL came along and really kind of brought engineering software to an affordable platform, namely Windows. And we were able to really, really leverage that, and that's where, back in the early 90s, really OpenGL and MFC, if you knew about those technologies, you could build a pretty compelling 3D application. In the kind of after about, and really that was the start of when the gaming industry really got a lot of momentum, and really where engineering was a driver of what the 3D vendors were doing. And really by the time you got to the late 90s, the amount of money that was being driven from the gaming industry really dwarfed what they were doing in the engineering software community. And what the gaming community wanted was more compelling visualization. They wanted to have more photorealism. And so what that brought about is the advent of OpenGL 2 and DirectX 9, and that's where you start hearing about shaders or GPU programmers. And that's really where graphics kind of changed from a generic skill to really a specialization. So you had guys who were able to go to GPDIS or some of these gaming conferences and really start taking some of these algorithms and really starting to create some compelling renderings, but by working lower level and having more direct access to the rendering pipeline, which is what happened with this kind of OpenGL 2.0 and DirectX 9. And that's by and large kept us going for the last 10, 15 years. And there's been incremental. We're up to OpenGL 4 now, and we're up to DirectX 11. And there's been minor iterations in what you can do from a shader perspective, but by and large, it's the same architecture. Right now, we have Vulkan, which is the next generation of OpenGL. We have DirectX 12. These are either in beta or coming out imminently, and these are to the next level of control with the data. And the challenge is that now what they've found is that the current architecture really isn't designed for mobile. It doesn't really allow us to take advantage of these high-resolution devices. So just like when we moved from OpenGL 1 to OpenGL 2, they essentially opened up the rendering pipeline. It's kind of similar in this next phase where they're really starting to open up direct access to the memory of the frame buffer. So we're going to be able to start doing a lot more with the data. We're going to be able to be a lot more efficient with using the data, but it's going to introduce a new level of complexity. And that's just something on the radar, and I think if you know, anybody who's a graphics programmer today is probably following closely what's going on in this domain, figuring out when they're going to you know, start jumping into the water with this technology. The next thing that's a really interesting trend and a good one is that where in the late 90s, you know, Windows was really the dominant platform, and you know, Microsoft was being pretty aggressive around DirectX. Frankly, DirectX is a pretty compelling technology, and it looked like OpenGL was going to go away. And really in that late 90s, in fact, at one point, Microsoft came up with pretty strong statements around OpenGL was going to be layered on top of DirectX, and as a result, there's going to be, you know, performance impact. And it really looked pretty shaky there for a while with OpenGL. But you look at what's happened in the last 15 years, it is the 3D subsystem on Android and iOS, and this WebGL technology came along, which is basically OpenGL. So now, suddenly, if you're talking about mobile, if you're talking about the browser, OpenGL is your only choice. And so really, and OpenGL is as vibrant on the desktop as it was in the early 90s. So now really, if you're looking at building a multi-platform solution, you know, OpenGL is hard. It's hard to argue about OpenGL not being the solution that you would invest in, which is really, really, really interesting. And the one caveat there being that Microsoft, although a little more open, do seem for getting onto these and their HoloLens and into their App Store look like they're still forcing DirectX. That may change, but for the moment, if you're looking to play in that domain, it still seems like DirectX is the better choice. So they're kind of like two generic graphics industry issues. The other things are, you know, just the technology landscape has changed under us. As I mentioned a little bit about WebGL, but you know, the Web 2.0 movement and this amazing concept that your application can be a web page was never something that was really viable for the engineering world because 3D wasn't supported by the browser. Well, now it is, and you know, I'll talk a little bit about it in a while. But you can build a pretty compelling 3D application in JavaScript and HTML. So that's a really interesting opportunity for us, and it brings the power of Web 2.0 and the ability to rapidly iterate, and it brings that concept into the engineering software world. And if you look at people like Onshape are obviously building their future based on that platform, gives them some competitive edge over the market, over what other people are doing, which is really, really interesting. There's also you know, it's a much more heterogeneous world from a hardware perspective. You know, 10 years ago, you wouldn't see a Mac, somebody using a MacBook when you go into a conference room. Now, when I go around in the engineering world, I see them a lot. So it's really just kind of bring your own device to workplace. It's really, we're dealing with a much more of a heterogeneous workplace. And so this multi-platform where, you know, in the early 90s, you know, you were looking at a multi-platform world in engineering software. You were all Unix, flavors of Unix. And it's similar today. You know, if you're looking at building a solution, you know, you got in many respects a more complicated environment that you're delivering to, because you have not just, you know, Windows and OS X and possibly Linux, but you also have this mobile platform, and you also have this browser. So this is a pretty interesting problem that we have to solve. Android and iOS, you know, I think we all see them as consumption platforms today. But if you kind of look out into the future, you know, I think we all see convergence in the future there. If you look at, I have one of these Google Pixel C laptop, or they're effectively a laptop, but it's running Android. So you're starting to see that these devices are moving out of the classic kind of phone, mobile form factor into these tablets, and these tablets are really starting to encroach on the laptop world, and so it's something that we need to be thinking about as we're doing engineering and building engineering solutions. The great thing is there's great new tools coming along, and Xamarin is this technology that Microsoft brought to the market. A company they acquired. It's incorporated with Visual Studio now, and the vision behind it is that you bring your C# development and use it on iOS and Android. So maybe you can write once and compile to these different platforms, which is very interesting. Another one is this scripting technology, which allows you to take your C++ code and compile it to JavaScript. So now maybe I can, and we use scripting technology internally. If you write valid OpenGL code, it will actually compile it to WebGL. So now you're starting to look what seems like a very complicated problem that maybe if I choose the right tools, it's not as challenging as it may be. The next one that's really interesting is this virtual and augmented reality. This is really interesting technology. The great thing is, unlike the past where they really were built on top of custom SDKs, it's actually quite easy for you to take your existing OpenGL system and drive these devices. And so, I've seen a very interesting conversation with the Microsoft guys when they were talking about the HoloLens, and the way they see it is they see it, in the manufacturing and the engineering software space, they see it as bridging the gap between, on your screen and 3D printing, where 3D printing gives this next level of engagement with your 3D design, but it takes hours to print out some of these small models. And while putting on the HoloLens, you can actually see it and have a more immersive engagement with 3D models, which is pretty interesting. And so they see it, their future is they see it as another window in your application. And so you'll have essentially running on the desktop, and you put on these graphs and you can see the model. And certainly that's kind of the same with the virtual reality world. So it's interesting to see how both of those technologies are going to play a role in the engineering software world. The good news being that they're using our technology that we're using today, so they're using DirectX, they're using OpenGL, and it's really just a little bit of low-level shader work that you need to do to get the stereo, essentially effect to these devices. And then the last point that I mentioned is just, we're seeing larger and larger models. Certainly, the cloud enables the federating of models, but you're also starting to see, because there's this consolidation within the engineering software market, people are bringing in data from different systems, and so we're really starting to deal with larger models, and getting them working is a challenge, and something we need to be continually aware of. So that's the kind of what engineering graphics is and why it's important, and then kind of talking about some of the essentially the trends going on in our industry. Now I wanted to quickly jump into talking about our products in the context of these of that. As you may know, TechSoft has expertise in 3 main areas. One of them is in data access. We allow you to read in CAD data without needing the CAD systems. Engineering graphics, which is what we're talking about today. And then 3D data publishing, including 3D PDF, but also going as far as HTML and standard formats, including 3MS. But I'm going to be focused mainly on our HOOPS Visualize and HOOPS Communicator products. So the first one is HOOPS Visualize, and this is the product which is our flagship product. And this is really about enabling building those applications I talked about at the start from a native standpoint. So if you're a C++ developer and you want to deliver an application on everything from all the desktop platforms, from Linux, OS X to Windows, over to Android or iOS, and HOOPS Visualize serves that need. It's really an application framework, so we see it as a platform rather than a component. So generally, when people install visualize, in their first day they have an application that is allowing you to load in 3D models, allowing you to select, rotate, pan, zoom, print that model, save it as a PDF. All these kind of capabilities are included so that you can very quickly focus on what your core competency is. So it tries to solve all the generic problems around building a 3D application. From a quick architectural review, one of the really important parts, it really breaks down into two layers. What we call core graphics. And core graphics is a graphics database. So you put your 3D data into this scene, and then we leverage the underlying hardware to render that device optimally on that system. So it uses OpenGL or DirectX, depending on which one is faster or which one is supported. And then, what's important for us is also, people do want to print out their models. So we support a strong hard copy pipeline. But this abstraction from the underlying graphic subsystem is what allows us to provide you with a unified API, which allows you to drive, a DirectX platform like Windows, but also an OpenGL platform like OS X or Android or some of these VR devices. So that's really where we see a lot of the IPs in this core graphics component. Then sitting on top of that, we built an application layer, and the application layer implements the standard functionality that you would expect in an application. So you can imagine all the camera operators. You can kind of think of markup and redline, all these kind of things that you generically do. They're all pre-written and provided to you and have a high degree of customization so that you can have them to match the capabilities in your existing application. Secondly, it also includes integrations to complementary components. So, for example, through HOOPS Exchange, if you want to load in a CATIA file, we can do that just by essentially using that integration. And what we do with these integrations is not just do a low-level integration, but once these things are integrated, you have a high-level interface to those objects. So, for example, if you read in a CATIA file through HOOPS Exchange, this application layer is going to have the ability for you to isolate a component in the assembly. It's going to have an interface to allow you to set a view in the model. And all these capabilities are included in there. So that's pretty important. And then, the starting point for our customers are these sandbox applications. So these are just really starting applications that people can look at and quickly use to build as a reference point for building their own applications. And we provide a large number of different sample applications and have one on every single supported platform, of which there are, I think there's 6 platforms if you count the mobile and all the desktop platforms. So that's HOOPS Visualize, and probably the most prominent customer is eDrawings, who we've been working with since 2000, and they've been very interesting because in that eDrawings application, as SolidWorks has moved beyond just design, so you can imagine they obviously had a strong need around 2D and 3D working together, but as they brought analysis into the SolidWorks world, they're able to bring that data into Visualize into their application, so that was really, really positive for them. And then over the years, they've actually brought that product from not just being a Windows application, but as also an OS X application and also an Android and iOS. And they actually just recently released the web version. So that's been a real good example of that partnership, which over the years, because we've been focused on this engineering graphics problem, they've been able to broaden the scope of this application with minimal effort on their side. The other product I wanted to talk about is HOOPS Communicator. And HOOPS Communicator is similar to HOOPS Visualize, except it's more targeted at HTML and web developers. And because it is essentially a web development studio, it has a much stronger client-server architecture. So it has a very scalable and modular architecture. The actual viewer is very engineering focused, so there's a very professional viewer that's included with it. You can see a screenshot of it on the right, but it includes measurements, it includes a full model browser, this is a model browser which is responsive, which means that if you run it on mobile, the viewer will configure it to that mobile device. If you run it on a desktop with more screen real estate, it will handle it. It handles touch. The viewer works on not just on a browser, on any platform, so everything from mobile to desktop. And one of the key elements is dealing with large models. So this can really scale up to large models. And in fact, Jonathan will be giving some examples of this shortly, but it does what's called resource limited. So if you really have massive models, that most browsers unfortunately are 32-bit browsers, if you want to constrain and say, hey, I don't want my applet to use more than 200 megabytes of memory, it will, through streaming, load and unload data into the system. So you can really get to very large-scale models. The architecture really comes down to 3 different elements, and 2 of them are on the server side. So the data authoring, you can author data by just providing CAD data directly in, and in which case, we can take a CATIA file and it'll get converted into a model, or you can directly author the data. So if your data is not a file and you're just authoring from your own application, you can do that by directly authoring the data. Once the data is authored, then we have a server component which streams that data down to the client. So that allows for this, in the web space, a really important part of having a responsive application is that, very quickly people see data. And particularly with these CAD models, which are very dense from a triangle standpoint, you can't just wait for the whole model to be downloaded. So we have this streaming mechanism, and the HOOPS server component is what does that. And the interesting part of it is that the viewer can work in fully leveraging the GPU on the client, so that's where it's using our WebGL, or it can actually run on the server. And if you wanted to run on the server and leverage like the grid, NVIDIA has the grid technology, which is the GPU on the cloud, it can use that too. So depending on which one you want, it can do the server-side rendering or the client-side rendering. And that's all done by the web viewer, which is, as you would expect, a modern architecture. So it's all HTML5 compliant, very engineering-focused feature set, which Jonathan will show you shortly. And the really nice thing, this has its own API to it, so you can build an application on top of that. And the API it allows you to seamlessly move between client-side graphics and server-side graphics. So you can build your whole front end around this web viewer, and then just with a switch between WebGL-based, meaning client-side graphics, or server-side graphics. A good example of a partner is GrabCAD, who we were the engine who brought in the CAD data and provided this 3D player. It's they're getting tens of thousands of models a week, and are a really great partner to work with. But all the technology around the translation and the viewing within that platform is built on the Communicator platform. So with that, I'm going to hand things over to Jonathan so that he can kind of demonstrate some of the things I talked about.
All right, great, Gavin. Thanks. Thanks for that. This is Jonathan. I'm going to show my screen here in just a minute, and we're going to show a couple of those things that Gavin talked about in some of our different applications. So first, what we wanted to do was show some features of HOOPS Visualize, and this is our desktop and mobile-based graphics engine. And we're going to start real basic, but this is important for engineering graphics. And so even though we're all excited about virtual reality and being able to run on those architectures, still a lot of the data out there is 2D graphics, and we got to make sure that we support that with good text, anti-alias text in a font engine, as well as hatch patterns within your 2D drawing. So here I've loaded a CATIA drawing file of a landing gear model, and we're able to load that in. All all my hatch patterns come in with proper booleans if there's interior loops that need to be cut out. All of my line patterns, that's again, when it comes to engineering graphics, you want to make sure your line patterns are accurate. You just don't have solid lines, but your line thickness is accurate, as well as the pattern of the line as well, in terms of the dots and the dashes. Many times, maybe out in manufacturing, or if you go into architecture or GIS, that pattern is super critical, and it's important for the interpretation of that drawing. In fact, there's regulations that dictate what that can actually be. So we're able to support that. All of your layers with HOOPS Visualize, we're able to support that. This is the HOOPS demo viewer, and it's based on the HOOPS Visualize. I was able to read in that CAD data using HOOPS Exchange. So there's this tight integration between all of our different SDKs. HOOPS Exchange allows me to read different 25 different engineering file formats, including that CATIA file, Pro-E, Solid Edge, SolidWorks. Here now, though, I have the master model of that landing gear. It's the 3D model, and so we start talking about, well, what does that look like? In CATIA, they do a fantastic job with annotating the model with different pieces of information on how to manufacture that. So I can activate different views that isolate parts of that manufacturing information that allows me to then go in and instead of using 2D drawings, I can just use, hopefully as we go to a drawingless type of manufacturing environment, I'll be able to just use this master 3D model and step through the different PMI views that allow me to manufacture that. But in order to do that, you need good tools to be able to interrogate your data. So not just good view management and being able to represent all of the data, the PMI data that existed in the original CATIA file here within your own viewer, but being able to link that. So if I select on a piece of PMI, being able to link it to a feature, as well, this very simple pieces of information, like if I was to rotate this, all of a sudden the PMI still is not backwards, but we have something called flippable PMI, and when you create a graphics engine, you want to make sure that you have all of those very small nuanced features, but in order to create a compelling application, you want to make sure you have a set of tools that just have that for you. So here, if I was to click on different pieces of PMI, then it highlights the particular features that it's associated with. So that's the 3D model there. Moving a little bit further, we'll look at a different model here. This is a Pro-E model, just a part of a much larger assembly. When we are able to read this data in, I can select on a particular edge and get the associated data from the CAD file with that. So that might be persistent IDs, the actual surface area of a particular face, any material information or naming of that particular part. So having that selection, and then also the callbacks when you develop an application to go back and get that original data from the CAD file is very important. But the larger the file that you load, the slower selection may be. And so within HOOPS Visualize as well as HOOPS Communicator, we have very fast selection. So here I'm able to hold down my Shift key in this demo viewer and automatically just select whatever's underneath the cursor. And this allows just me to demonstrate how quickly we can select in a moderately sized part file, but even much larger assemblies, we're able to do very, very quick, both graphical and analytical selection. Gavin also mentioned point clouds. We see a lot more of this data, excuse me, when it comes to metrology or in architecture. So we're just getting so much more scan data, and we're trying to marry that with graphical data. And we want to make sure that it looks good, right? So here's a bunch of points. It's a million points representing that engine block that we just looked at, and it's not super intuitive because it's just a bunch of points that I'm rendering here on the screen. Well, with some of our advanced shader techniques, we're able to infer a normal or how light bounces off those points on a surface, and all of a sudden I'm able to get, again, depth information visually, visual cues that are so important to be able to interrogate a particular object when I apply this eye-dome lighting technique onto that set of points. And all of a sudden, now it's data that I can start to work with and maybe measure, interpret, or to project onto the original surface and do a measurement, deviation measurement from that. So that's just some of the features of HOOPS Visualize. We have a whole library of tools that help you build compelling applications both for desktop and mobile using HOOPS Visualize. We're going to shift gears quickly and look at, well, what does this look like when it comes to on the web. And so here I'm going to demonstrate some of the new features of HOOPS Communicator. So there's, again, a whole tool set of different tools within HOOPS Communicator to be able to visualize and interrogate and create very compelling workflows within a web browser. This is a zero install. So there's no application that's been installed here within Chrome. I'm just hitting this web page, and I've said to load the assembly tree of a 600 megabyte ProE file. In fact, that engine block, we'll see it here in this assembly. But if for some reason I had very limited bandwidth, I don't want to load all that data. Now, when it sits on the server, we convert it to a visualization format. It's not 600 megabytes anymore, but we're able to thin that down to about 10% of the size, but 60 megabytes could still be a significant amount of data to stream. Now here I've just requested a sub-assembly. I haven't requested the whole assembly, but just the chassis and the wheels. I can continue to request on demand the drivetrain. So here came my engine and my transmission, my drive axle. All that came in as well. And then if I wanted to load the entire model, I could, again, on demand request that sub-assembly. If I wanted to, I could have drilled down further and requested just maybe a particular part. There's other options here as well. We can reauthor the data. You might have noticed in my context menu, there's different mesh levels. And so if we author that data with different levels of detail, you can request that as well. So what we're trying to do for very large assemblies, as data gets larger and larger, we're trying to make it scalable within the confines of technology as well. So data out there is huge. How do I visualize that in real time on multiple devices? Let's look at a few other workflows as well. So here I'm going to just look at the side view of this particular car. And imagine I wanted to create a configurator that switched out different parts of this car. If I wanted to have different rims and tires for performance reasons, or maybe visually, I wanted to see, well, how can I reconfigure this to mimic, maybe I wanted different ground effects or put a different suspension. And we see a lot of online configurators now as well, in a number of different fields, so not just automotive. But here we have 5 different types of tires that we're able to load it in real time and configure this. I could swap out hardware, the engine, or obviously change the colors. And so all of that here is within the API, you're able to do that in HOOPS Communicator. But let's take a look at something else, a different workflow possibly. Here I've just isolated the engine, and if I select on a particular part, we've created a workflow that says, all right, we'll make the engine block transparent, and we also have some additional data outside the confines of HOOPS Communicator. We've taken this particular piston, we've loaded it into one of our partners, SimScale, into their FEA analysis tool, and we've done some steady state heat transfer analysis on this particular part. So we've applied a heat load to the face of the piston and some constraints on how heat dissipates through the piston, and calculated the steady state heat transfer. I've taken that, we've mapped it to a color map, and then just applied that to the vertices of a meshed version of that piston, and displayed it here. And so you can imagine different workflows for different industries. So it could be metrology. You want to see real time what's going on the shop floor as you're measuring parts, maybe deviation over time of your manufacturing machine. It could be architecture, it could be automotive, it could be aerospace. There's a lot of different possibilities there. Well, let's look at a different workflow here. I'm going to load in a 30 gigabyte Boeing 777 model. So again, we've converted this to a form that HOOPS Communicator is able to stream in, and we're doing something called delayed real-time loads and resource constraint visualization. So we've maybe put a cap on the amount of data that we're allowed to visualize here within this viewer, and streaming it in real time. If we hit that cap, we stop streaming. Or if we go to a particular view, if I say kind of isolate the turbine, I'm streaming in data that's just related to where the camera's looking, and so the rest of the model is not being streamed in anymore, but instead I'm just bringing in data associated with the bounding information of what my camera or the viewport is trying to look at. As well, if I wanted to, I could go to a different part of that model, and now all of a sudden I've stopped bringing in data for that turbine, but instead here I'm bringing in data for the inside of the cockpit. And this allows me to now visualize very large models within the confines of maybe a 32-bit browser, or maybe even a mobile device that supports WebGL. So this is a new feature of HOOPS Communicator 2000. Well, it was 2016 Service Pack 2. Now we're on 2017, and it's something that allows you to be able to visualize your larger and larger data. So there's a ton of stuff to demo. If you want to take a look at some of these, the HOOPS demo viewer is available from techsoft3d.com. You can request that. We're also very happy to share some of these online demos with you as well. After this, we'd be happy to follow up with you and give you a live demonstration or evaluation of these SDKs. That's all the time I have for demos. I'm going to turn it back over to Gavin and James now.
All right, thank you very much, Jonathan. That is a great demo. Appreciate that. And now we're going to wrap up here, and Gavin is going to start us up with a summary.
Do you want to do that? Oh, yeah, so I think hopefully, thanks for that, Jonathan. They look great. So I think that the first thing, just on some final comments would be, I think we're in the engineering graphics world, we're in a fantastic place today. We have this fantastic hardware that's available to us, and so it's allowing us to really create extremely compelling 3D experiences for our customers, but it's complicated. Is the challenge, and it's we're just particularly with this new evolution of these APIs, where it's just we're at a phase where things are getting complicated right down at the raw 3D level, and it's just a complicated set of technologies out there with respect to building some of these web applications. And here's the I guess the plug at the end is that this is the problem we're trying to solve. We think we do a pretty good job. So there is a set of technologies out there. If you're using them today already, hopefully you're finding that to be the case. But if you're not, we'd love you to come in and have a look at the technology and see if it's something that you can help you kind of achieve your product goals.
Okay, thank you, Gavin. And now it's question and answer time. And we have our first question here is, could you create an application like Onshape using HOOPS Communicator?
So Onshape is a very advanced application, and so some of that really low-level editing and sketching of the data is not something that we support right now. So generally, you can have a connection between a client and the server, and you can change parts, but the kind of work around low-level sketching, which has some constraints, there's a lot of complexity around having that work very efficiently, that's not kind of solved down at our level. So I would say the level of editing that you're doing in the SketchUp with that low-level geometry editing is a challenging problem to solve and requires some of these constraint engines which we don't support. But with Communicator, you can create geometry on the client side, you can move things around, and so all those kind of edit workflows are supported.
Okay. Thank you. And the next question here is, do you support virtual reality today?
So we've been playing around with both virtual reality and particularly the Vive headset, as well as augmented reality and the HoloLens technology from Microsoft. We have our technology running on those today, and we have packages which we are making available to select customers, and we're expecting to roll out official support this year. So this is kind of just new technology coming to the market, but it's certainly part of our roadmap for this year. And we have, if you're a partner today, we do have some technology that we can share with you that would allow you to kind of start playing around with the technology. One of the challenges with AR and VR is that it's not so hard for us to get our technology working on that platform. The challenge is that a lot of what Visualize supports and Communicator is around the user engagement. And if you look at, you have these different sticks that you're holding in the 3D space, and so what do our operators look like? So it's been easy for us to get our camera and walk around the scene, but then what does it mean to select an object? And these kind of workflows are kind of, we're still trying to wrap our hands around how we would provide an interface to that, those kind of capabilities to our users. We may just allow them to go straight to the interfaces from OpenVR or HoloLens, or we may try and wrap things up, and that's where we're kind of at today.
Great. Thank you, Gavin. That's all the time we have for today. If you guys have any further questions, please contact us at info@techsoft3d.com, and we'd be happy to engage with you and help you create stunning and vibrant engineering graphics. Thank you very much, and have a great day.